Hello everyone, welcome to the webinar. We're just, there's still some numbers building up, so we'll just give it a minute before we kick into the main event. Oh, that's built up nicely now. Okay. Kia ora everybody, my name is Ben Riley and I'm a Sector Engagement Partner here at Toitū Te Whenua Lens. Welcome to this webinar today for the 3D Coastal Mapping Program. To give an introduction and overview to the program, I will just start with a karakia. Te mata tātou, whaia te mātauranga, kia marama, kia tupu, kia tiaki ngā whenua, ngā moana, ngā arawai. Kia whaitake ngā mahi katoa, aroha atu, aroha mai, tātou ia tātou, toi te kupu, toi te mana, toi tū te whenua, homie, huie, tai kie. And that's just to say that we pursue knowledge for understanding, developing, and caring for the lands, the bodies of water and the waterways. We seek purpose in all that we do. Let us show respect for each other, hold fast to our language, hold fast to our spiritual strength, sustain the land, gather and go forward together. A little bit of housekeeping. We have a Q&A function in the chat today, so feel free to pop in your questions. And then in the second half, after the presentation, there will be dedicated Q&A time. I'll be fielding questions to Stuart, who I'll introduce shortly. And also the webinar is being recorded and we'll be sharing it afterwards. Expect that to be shared within about a week. We'll just get the video tidied up and some captioning done. So it's nice and a nice viewing experience before we share it. And without much further ado, I'll introduce Stuart Kai. Stuart is a principal geospatial specialist working at Toitū Te Whenua Land Information New Zealand as the program lead for the 3D Coastal Mapping Program. Stuart joined LENS in 2006 and led the National Hydrographic Survey Program to update the nautical charts for Aotearoa New Zealand and some Pacific Island states. He has also led the delivery of a New Zealand aid program to improve navigation safety in the Pacific region. Stuart, kia ora.
Kia ora, and thank you, Ben. And good to see a good number of people joining us online and having an interest in hear about this exciting program of work that we have running at the moment. So just to give you an overview of what you're going to hear today. So we're going to be talking about what we are doing, where we are doing it, why we're doing it, how we're doing it, and what the benefits to New Zealand are. So in terms of what are we doing, if we kind of turn to a bit of an overview of key and connected projects that LINS is working on to realise a vision of seamless mapping across land and sea, to improve modelling, particularly to model the impact of coastal flooding from storm surge, tsunami and sea level rise. So one of the programs there already highlighted in a box is the National Elevation Programme. So LINS has been coordinating the collection of topographic LiDAR, which has been mapped by regional councils, and we're about 80% of the country has been mapped and counting. Another piece of work is HighPlan, or our long-term program for seafloor mapping, primarily to update our nautical charts to improve safety navigation around our coast and support international shipping and trade. Generally, the surveys go into water depths of about 5 to 10 meters to keep the small boats and personnel safe, not getting too close to uncharted rocks. And then kind of what we want to focus on today is the 3D coastal mapping. So this is the program that really fills the gap between those two programs, and this is a national adaptation plan initiative that was developed in collaboration with the Ministry for the Environment. So it's all well and good having all these different data sets, but a key and critical part of this work will be this part joining land and sea, and this really is a way of being able to join different data sets together, data sets that are on different vertical datum, so they have a different starting 0 point. For the land stuff, maybe more around mean sea level, whereas the charts and the Bathy data is around lowest astronomical chart. So joining land and sea is a complex piece, and it's going to involve producing a tool that's going to help users to merge data sets together all onto the one common datum. So focusing on 3D coastal mapping, which has two streams of work. One is mapping the coastline, and the other is installing and upgrading satellite positioning equipment at tide gauges around the coast. That's really going to measure the land movement up and down, and we'll get a little bit more of that shortly. Okay, so where are we actually doing this work? So this image shows the areas that we've identified for mapping. We've gone through a process of bringing together information about population, location of roads, railways and power lines, and also taking into account the elevation of land. So the scope of the work is to map 200 meters inland of the coastline, which will overlap with the topographic LiDAR data, and then seaward to around about the 25-meter water depth. We've had conversations with stakeholders to check and confirm these areas and that they're appropriate and they kind of fit in with their thinking. And also through these conversations, we've identified other areas that we may be able to have possibilities or opportunities to partner with stakeholders to include in the program. So there's still a little bit more work to do on some of those, but this is where we are. This is where we are starting from, and work has commenced already. So the other stream is the GPS at tide gauges, so global positioning satellite receivers installed at a number of gauges. So you may be familiar with the term tide gauge. These are sensors that record the rise and fall of the tide around the country. Gauges are usually located within ports, have been operating for decades, and this data shows how sea level changes over time, which is only really half of the story when you want to understand the impact of sea level rise. So using the satellite positioning receivers installed at some of the locations all close by, we're able to record the vertical movement of land, which coupled with the sea level data improves our understanding of relative sea level. And one of the projects that is making use of this and has already done some work is the NZ Sea Rise program. And this gives more information on this. And just to follow here is a short video provided by some of the experts involved in that program.
Global mean sea level is about 3.5 millimeters per year of sea level rise. That's the average rate around the world. And in some places around the New Zealand coastline, the land is subsiding twice that much, or it is rising twice that rate. And so when the land is subsiding at the same rate sea level is rising, you essentially double the amount of sea level rise. And where the land is uplifting at the same rate sea level is rising, you cancel out the global sea level rise. So vertical land movements, or VLMs, as we call them, matter when predicting sea level rise.
Okay, so just to kind of recap on that, then obviously the importance of having these two data sets joined together to understand the change in elevation of the land, but also how does that relate to how sea level is changing around the coastline. So moving on to why we're doing this, I mentioned that earlier there was a vision of seamless mapping across the land and sea to improve modelling of the impact of coastal flooding. At the moment, over 80% of New Zealand is mapped with topographic LiDAR, so on the land, and that gives us a good understanding of the shape of the land. We don't have the same level of coverage for the seafloor, and intertidal zone can be hazardous for small boats mapping in the seafloor area. And as I said before, all of our offshore surveys generally start around the 5 to 10 meter water depth. So for those users who carry out the modelling, having a gap in the data coverage can impact the accuracy of any outputs, any results from that. Hence, 3D coastal mapping aims to fill in the gap improving the outcome of the modelling and provide greater certainty on the impacts of flooding. So the project will significantly improve baseline data upon which resilience to coastal hazards and climate change impacts can be assessed and mitigated. It will provide improved data to identify coastal areas at significant risk of flooding, tsunami and inundation, and really help communities and local and central government to plan and adapt to climate change induced sea level rise and more frequent storm surges. It also helps to understand the impact of natural events such as earthquakes on natural environment and infrastructure. So by a way of example, following the 2016 Kaikoura earthquake, topographic and bathymetric LiDAR was collected along the Canterbury coast and followed by an acoustic bathymetric survey from a small boat just offshore. And this graphic here shows that combining of data sets, bringing them all together to identify, in this particular case, the Papatia fault line running from the land to offshore. The data was used and useful for MPI in understanding the impact on the marine habitat, especially for paua and crayfish, which were once underwater but are now above that waterline. And of use to Wakatahi in determining where the new coastline was and safe elevation above the waterline to support with the road rebuild work. So without going too deep into the technology that we're using, that could be a subject for a later webinar. I'll touch on some of the mapping components that we are using. I'm also conscious that there may be some experts with very deep knowledge on this, so hopefully I get it right. Okay, so we're using a few different techniques on this project. Mainly it's LiDAR, or light detection and ranging, which is a remote sensing technology that uses lasers to measure distances and create 3D maps. LiDAR systems emit a laser beam and measure the time it takes for the light to bounce back from the surface. Combining this with other data recorded on board the plane, then it's possible to generate precise three-dimensional information about the shape of the Earth and its surface characteristics. A LiDAR instrument principally consists of a laser, a scanner, and a specialized, very precise GPS receiver. And sensors are normally fitted onto aircraft or helicopters to give that better coverage over wider areas. The two types of LiDAR, there's a topographic and bathymetric. The topographic LiDAR typically uses a red laser light to map the land, while the bathymetric laser is green, which penetrates the water and measures the seafloor and or the riverbed elevations. We're also using satellite imagery to extract water depths, and this is known as satellite dry bathymetry, and we'll touch on that a little bit later on. And then finally, where the LiDAR is unable to fully map the seafloor, particularly in areas where there is high turbidity, so a lot of sediment in the water, where the laser light can't penetrate to the seafloor, then we're planning to use more traditional acoustic multi-beam sounders in those areas. So we've contracted two companies, Woolpert, they are flying around the North Island, or have been, and NV5 company are mapping the South Island areas. The work started in February this year, and the season is coming to an end as the autumn weather really kicks in. Both companies have been making great use of the good weather and been following around the country to chase the sun, find out go where the weather is good, and reduce turbidity. So we've approximately covered about 30% of the scope so far in completed. So that's around about 3,000 square kilometres. And this is the area that has been completed data, and there's no further LiDAR work required. So the image on the left there, a little video taken inside one of the aircraft, so you can see it's quite cramped. Certainly no Koru error on board that plane. So just give you an example of some of the data that is being produced and what we are looking at. We've been working with the suppliers to review the data to check on the coverage and really where to focus efforts to refly areas. Here off Brighton Beach, just south of Dunedin, you can see some of the gaps very close into the beach. So this is where the surf is making contact with the beach. And then maybe a little bit further offshore, you can see some gaps which are likely suspended sediment or high turbidity in some of the deeper troughs of some of the features further offshore. So the offshore here is really the maximum depth of the scope, so around about 25 meters. So we are achieving that depth in many places. So in areas of high or persistent turbidity, and where necessary, then we're planning to infill with our acoustic bathymetry survey work. And then just another example, this around the North Island. So high here. Of the data showing a rocky outcrop, as indicated there on the chart, east of Whitianga. And just give you an example of the data, what is being produced. So in the bottom profile line there, you see the yellow-pink line is the sea surface. The blue line is the seabed, and seeing some of the shapes of the rocky features. And then the yellow dots to one side are more likely a school of fish. So picking up quite a bit of detail of the seafloor, and also what else is within the actual water column itself. Now I've talked about satellite dry bathymetry, or mentioned it earlier. So for areas outside where we're mapping with LiDAR, then we're looking at another technique, satellite dry bathymetry, and this is using satellite images to be able to extract the water depth. So rather than using an active light source like LiDAR, and using satellite dry bathymetry really relies on the passive light of the sun to illuminate the seafloor. So generally speaking, if you can see the seafloor, you can derive a water depth. And we've been running a trial in the Bay of Plenty area with some success, and we're now looking to use this elsewhere. So turning to what are the benefits from coastal mapping, particularly for New Zealand, and really looking at the improved decision making around resilience. What's the impact? How can community government respond to forecasting and the impact of inundation? How can this information be brought into spatial planning? A way of reducing cost of damage and loss of assets or infrastructure to productive land as well due to coastal hazards, and being able to have better zoning and planning decisions. There's also cost savings for reduced damage to coastal buildings and infrastructure, and all this is attributable to the decisions that are based upon that more accurate hazard prediction models. And then in terms of economic and environmental benefits, this supports regional development projects, road and rail infrastructure resilience, faster growing and more productive aquaculture industry, which maps the nearshore seabed, providing investors with a better information to make decisions around location of such structures. And it's really enabling better and more enhanced modelling, providing a better understanding and forecast of the impact of significant flood events and impact of sea level rise. And then touching on other use cases and using data can be used in terms of with GNS Riskscape, so a software tool that assesses the risk to people, buildings and infrastructure from the natural hazards such as earthquakes, landslides, volcanic eruptions, tsunamis and floods. NZ Sea Rise, these maps show sea level rise and the vertical land movement as we saw in the video earlier, and incorporated under potential climate change scenarios. And then Coastal Change, where the project that aims to improve the understanding of the rates our coastline is changing, either eroding or increasing, and what threat that has to our communities. So just to bring you some examples of the data again, and how we would see this being made available. So this is a representation of some data around Cable Bay provided by one of our suppliers. Showing the elevation with the colorized points over the elevation, a way of representing the data to be able to visualize it. And we're also provided already a mean high water spring coastline, which has been published on the LDS. So this is a coastline that is useful for a number of purposes within resource consent or other activities within the marine reserve, and also in terms of cadastral surveying. So this is a pilot data set that's been issued based upon topographic data and also separation value between a mean high water spring line and also the datum that the LiDAR data was collected on. The intention with 3D coastal mapping is that with this data, we're then able to update and improve the coastline with more data, and that will be an ongoing process. And then, just as we have with the topographic LiDAR elevation models, the data will be made available through the LINS data service. So LINS data service, similar to the topographic LiDAR, data should be able to be downloaded and used. And also being made available on the registry of open data on AWS, again, very similar to what's already happening with some of the LINS data sets, such as aerial imagery. And then finally, and eventually, we wanted to get this data pushed out through our LINS base maps, which allows users to access the data via an API to incorporate it in some stunning visualizations to really support any decision making and planning that may be required. So thank you for your attention for this. Certainly open to any questions, and maybe just hand back to Ben to be able to moderate those. Thanks very much.
Kia ora. Thank you, Stuart. We do have a couple of questions coming in. One quick one. So do we have you've just mentioned the where in terms of the channels that will publish data through. Do we have an idea on timeframes?
Yeah, so
data publication.
Yep, so the first areas have been completed areas. Processing, realistically, I think going to be looking another couple of months before the data is coming back into LINS for us to do our QA process. So from certainly June onwards, we will be making that data available through those various channels.
And so the mean high water springs that we've just published into a pilot layer, do we know how frequently that might be updated going forward? Once it's out of pilot to start with, and then frequency of updates thereafter.
Yeah, not too sure if there's an actual schedule for that, but we would certainly be looking at any new data that could be incorporated into it, looking at mechanism, more of an automated process to be able to update it with new data as that becomes available. So it may initially start out as being a 6-monthly process, but that may decrease as the processes become a little bit more familiar, and we're able to automate some of those processes.
Fantastic. There's a question about the Pacific, where we do we do nautical charting, and a question about whether in future 3D mapping will extend out into the Pacific. Now it's not part of this program per se, but are we talking to Pacific Island nations and sharing, learnings with them and the like?
Yeah, certainly sharing our learnings and technical advice, expertise. A number of the Pacific Island countries have already undertaken similar work, certainly for climate change purposes, with a combination of bathymetric topographic LiDAR. We know of later the Cook Islands, there's been Vanuatu. So throughout the Pacific, that has happened for a particular purpose, a very similar purpose. LINS has been involved with some of the specifications for those work. So not necessarily doing the work ourselves, but certainly supporting the countries in getting the work completed.
You mentioned at the start that when describing how LiDAR works, that it was using green lasers. Are you able to talk about why it's green lasers and not, say, red or blue for this coastal application? Might be a bit technical, but
it might be a bit technical for me. Yeah, I wouldn't want to say anything while there are experts listening. So we may need to defer that and respond to that question once we tap into some more people with a greater experience.
Yeah, or if I feel like there are some people from our suppliers in the audience. So if I think they can respond in by text to that question that's in the Q&A. So yes, if someone would like to, do feel free to jump in, but we'd also might cover that in a later, more technical webinar.
Yep.
And will we be alerting councils of when data for their in their regions is becoming available?
Yes, absolutely. So we've had we're providing regular updates to the progress of the project to councils, stakeholders, and certainly there will be more targeted comms to those councils and regions where the data is becoming available, and making sure that they're able to use it. So what we're really keen to do is to get people to use the data. So it's all good, well and good collecting the data, but we don't get the benefits until this data is actually used, and we can see that. So we're very keen that councils, GNS, NIWA, other organisations are able to take this data, use it, and then show the benefits of what it's being able to provide to them.
Yeah, and I guess before that, in the collection phase, I think some councils have, as we've contacted them initially, have said, oh, could we capture this extra area? We've got a bit of budget we could potentially contribute, and we've been happy to
Yep.
collaborate on that. So
yes,
yeah.
So those are opportunities that we're certainly keen to look at and make the most of these assets when they're in country, because it's we don't necessarily have the full range of technology within New Zealand. So having this available at a particular point in time is our great value, I think, to others.
Nice. Sorry, there's a question here. Just let me read it. How have the results been for collecting nearshore information in high energy gravel coasts? So mixed sandy gravel beaches in like Canterbury, Hawke's Bay. Yeah, does the turbidity issue become an issue there? I think is sort of the underlying question.
Yeah, certainly. And so there's I guess two things there. You've got the surf zone, which a lot of white water and the light doesn't penetrate too well. So there are some gaps. I think I showed an example of an image of Brighton down south of Dunedin, where we could see some gaps in the data. So realistically, you're looking at, do we fly back at a different state of the tide, different weather conditions to try and fill in some of those gaps. In areas where there is turbidity, then again going back at another state of tide or another, avoiding any weather events that would stir up sediments, rain events that would cause sediment runoff from rivers. So avoiding those periods, those events, and again just taking a review of how persistent is that suspended sediment, the turbidity. If it's going to be there for a very long time, or it's going to be recurring, then do we look at putting our efforts in mapping elsewhere or reflying elsewhere to get better value, and then that becomes a program of work, say for a small boat to go and collect multi-beam data in.
And Murray's asked a related question: what depths are we able to survey in highly turbid areas? But I think it
varies. So the scope is out to 25 meter, and we've been achieving that and deeper in some areas. But certainly we're conscious of areas of high turbidity. We're just not going to get it. So we either, as I say, just put efforts in elsewhere. So I think fair to say that our suppliers are taking note of monitoring weather systems as they come across the country. Then maybe as you saw from the diagram, they are kind of bouncing around the country to make the most of the best of the good weather.
Yes, that's a good point. So we did have some areas planned for the first season, but the weather sort of dictated events, and our suppliers were chasing the good weather. So there's a couple of questions around sort of the satellite derived bathymetry, and how well that is working, and also sort of the comparison with the LiDAR in terms of resolution. How do they compare? Or how well does it work to start with, and how does it compare to the LiDAR?
Yeah, so satellite derived bathymetry, we're tapping into some readily available imagery that's of 10-meter resolution. So you can get that's easily accessible. If you want to go higher, then you're maybe paying a little bit more for that. So the resolution 10 meters, so far less than the resolution of the LiDAR. You're getting a high data density point with LiDAR. With the satellite derived bathymetry, you're able to also bring in some existing bathymetry that might be of a higher accuracy and resolution, and then use that to a certain extent train or improve the accuracy of the satellite derived bathymetry and the process that you run through. So the vertical accuracy, not necessarily as good as the LiDAR data, but certainly in areas where we don't have the LiDAR data, it's fitting in very well, and we're getting some reasonable correlation between the satellite derived bathymetry and also the LiDAR data as well. So we've been trialing it in the Bay of Plenty region with some good success, I think, and then we're going to be looking to pushing that out in other areas. Obviously, again, it only works where you can see the seafloor. So again, in high turbidity areas, then it's not going to be used. So we'll then be focusing our efforts in identifying those areas where this will be of value, will be of use, similar for the LiDAR, and focusing our efforts on those areas.
Terrific. Lots of that about the resolution. A bit of an easy one about our suppliers. Whereabouts are they based? They're both well, some with a New Zealand footprint, but internationally based, aren't they?
Yeah. So Woolpert, they have a New Zealand office in Napier, and they've been doing a lot of work with topographic LiDAR as well, and MV5 again. So they're a US-based company, but both using Kiwi-based aircraft suppliers. So in the North Island, Kiwi Air, and then South Island Land Pro. So with that, a Kiwi context.
Nice. And are we able? I'm not sure if we're able to share the cost, the average cost per square kilometre of I guess both technologies, the LiDAR and the bathymetry, for a comparison.
Yes, we could figure it out off the top of my head.
Might not be at the top of your head.
But, yeah. No, we can figure that out.
And someone has just answered that about the laser question. The green penetrates the water. Green wavelength penetrates the water, whereas red or near infrared used in traditional topo mapping gets absorbed. So that's why the green laser is used. Are you able to talk a little bit about the QA process for the data and how that's managed?
Yeah, so we're tapping into existing QA/QC procedures within LINS. So the data sets are very similar to the topographic LiDAR, and deliverables are very much the same. So leveraging off that workflow to be able to receive the data, and then a team within LINS will be reviewing the data, comparing against specifications, just to make sure that what we're receiving meets our requirements. We're pretty comfortable that we're achieving that. Just in the fieldwork collection, we're having regular contacts and discussions with our suppliers on a weekly basis, and running through the data as well, just to identify any issues. And so the process will be managed in-house, and then obviously with the output is being the deliverables then being pushed out onto the various channels, LDS and base matters eventually.
Awesome. Do you think so? This is a bit of a post, moving into a bit of the use after collection now. So do you think there's a couple of questions coming through? Do you think the satellite derived LiDAR will also be useful in like a post-disaster scenario. Maybe there's a couple of parts to that, like can it be collected quite quickly, readily available in the event, and how useful is it to use?
So satellite drive bathymetry, yep, certainly there are. We're testing or trialing out an online application where we're able to access imagery and relatively quickly and easily derive the bathymetry from that. I think it would depend on the type of event and how clear the waters are. Certainly, if there's any shake-up, any sediment in the area, then that's going to be the issue of it's not going to be of use immediately afterwards, and there might need to be a time for that sediment to settle down before we can actually use that approach. But certainly, using it post to determine any change, detecting any change immediately afterwards, but also the technique could be used for long-term change detection, and certainly it's a more available tool to access and use to be able to do that work within a relatively quick period.
Nice. And I guess a slightly longer term, and it's how will this information be? So it will be available. We talked a bit about the channels, and we can share the links to those channels to access that data. But I guess how useful is it for assisting coastal townships and marae in sort of the time frames that they might need for retreat? And I guess that's where they get, the data gets picked up by those models that we showed.
Correct. Yeah, that's right. Yeah. So we're really that providing the data, collecting the data, and making it available for those to really be able to use in modelling and adding into other existing data sets to improve modelling or expand it, and certainly in that the forecasting for the impact of any sea level rise or inundation or flooding, etc. So we're not necessarily in that space of doing the modelling work and how does showing and demonstrating in that, but certainly providing their data. But we will be very keen to work with people, organisations, institutes to be able to take this data and then see how well this supports any of that resilience work, what's needed in terms of adapting to changes, the coastline, what's the impact of a sea level rise of X millimeters or whatever over a number of years. What does that mean for marae, for infrastructure, etc.? What's the discussions that are then needed in terms of what's the next steps?
Yeah. Do you know how does the LiDAR scanning results translate across to programs like ArcGIS or QGIS? I think that's more of a data publishing question, isn't it? And how readily they can be picked up.
So certainly, maybe what I didn't mention was the data that's being delivered. So we're getting a number of digital elevation models, so very similar to the topo data, different resolutions, a 1 meter, 2 meter, and 10 meter resolution DEMS, a 1 meter resolution digital surface model, and then there will be the classified point cloud data. So all those data sets will be able to be ingested into various GIS applications, and we're also receiving the raw data, so which is, all intents and purposes, the waveform, which could then be used to extract further information if needed by those that want to maybe go into a little bit more detail, a little bit more information around what's in the water column, maybe identifying other features that haven't necessarily been classified as part of this program.
Yeah, and I think that'd be a good topic for a future webinar about the three channels we mentioned: the data service, the Lens data service, AWS Registry of Open Data, and base maps, and sort of the variations on publication through those channels and how they can be taken and used. So yes, for different applications. So yeah, I think that'll be a great future webinar. So did we, I guess this is a question about sort of the specifications, and so how did we land on a resolution for, I guess, mainly the LiDAR, but also the bathy, the satellite bathymetric data?
So the specifications for the LiDAR capture have been based upon our national base standards for specifications for topographic LiDAR. So again, keeping consistency across the data that we're collecting and with the very similar data sets, but for different purposes. So keeping that consistency across there, and then bringing into that some of the accuracy requirements that we have for hydrography and seafloor mapping, which is often depth dependent. So you need to be able to take in a depth component into that. So that's been brought in. We tapped into other nations' specifications and what they've used for similar projects. So we're not necessarily reinventing the wheel, but using what has already been used elsewhere to use. Simply with the satellite drive bathymetry specifications we've used before in the Pacific, and also tapping into other nations' specifications to be able to have some certainty and an understanding of what we're able to achieve with that technique, and then kind of gives a better feel for understanding the metadata that goes with it, so we can actually put some quality assessment around that data.
How did we mention at the start when we were talking about the program? How long is it in total? How long is the program running for?
Maybe skipped over that. So we started it a couple of years ago, I think, in terms of all the planning work and getting certainly the positioning systems at tide gauge is underway. The LiDAR mapping work started at the beginning of this year, and that goes through until middle of 2027.
Nice. And what are we able to say? There's some regions that we've been able to sort of capture in the entirety in this first season, and can be expected to be the first tranche published.
Yeah, so we had a priority area around the Bay of Plenty. We've been able to do maybe about half of that, I think, with weather condition, turbidity conditions, some of those areas. So that'll be a focus to get information out there. That was also our trial area as well. So we'll be bringing those data sets together for Tauranga Bay of Plenty area. There's also Doubtless Bay, Whangarei, Marsden Point, Bream Bay area are complete so they'll be looking to be published. Certainly that's what we are aware of at the moment. Certainly for the North Island, we're still kind of working on the South Island in the areas that are complete, and we'll be talking with our supplier around that as to where is complete enough before the weather closes in too much. But we got around about 30% of the scope complete, certainly with we're not needing to go and refly any LiDAR data.
Yes, so that's so the scope was to capture, if I can remember correctly, 40% up to 40% of the coastline.
That was the overall. So that total around about 10,000, but over 10,000 square kilometres. What we've collected so far is around about 3,000 square kilometres so far in their entirety, without having to go back and collect any more data with LiDAR. There may be a need to go back in some spots for filling in with bathymetry with a vessel, but that's still to be determined.
Fantastic. Well, I think that will the questions have petered out, and we're on quarter past the hour, and I think I'll move to wrap up there with just some closing points. So thank you very much, Stuart, firstly for the presentation and the standing up to the grilling of questions, exercising the knowledge in your head. So yeah, thank you a lot. Thanks very much. And yeah, I will move along. So as I wrap up, I guess stay tuned for that data to be published through the channels we mentioned, but also there'll be more more webinars planned in the future on other topics to do with this program. In the sort of next week, we'll publish the recording and all the related links to things that were featured in this presentation, including, I should say, including the video. I think it was from GNS that unfortunately the audience couldn't hear the audio for that, but the link to it will be shared for anyone wanting to go back and watch it. And I think it will also, it should be audible in the recording that we'll share. So through either of those ways, yeah, it should be viewable. But yeah, otherwise I will wrap up there and close with a karakia. Tamata tatou, kua e te kaupapa, ka re nā hua, ka rere nā arawai, kua mau te mātauranga, hei arahina ngā mahi o toitu te whenua, kia tau te rangimari e, ki runga I a tātou katoa, haumi e, hui e, tai ki e. Thank you very much, everyone. And we will be in touch again soon.